session, I just wanted to mention, so as you know, we are going for dinner on Wednesday, so tomorrow it's going to be at 19, so at 7 in the afternoon, and like, so, I mean, we're going to pass by this piece of paper, so you can sign your name and your dietary restrictions, so we are sure that the counting is correct.
That's the counting.
Okay. Welcome back, everyone. The second day of the second week of this workshop. This morning we have Paolo Arnaudo from Southampton telling us about gravitational perturbations of asymptotically AdS black branes and multiple polylogarithms. Please, Paolo, take it over.
Thanks very much. Let me start, first of all, by thanking Cristoforo and Robin for organizing this very nice workshop. I enjoyed very much the time here, and also it's nice to be back in Trieste for a while. So yeah, as Enrico mentioned, okay, this is the title of my talk. There are several ingredients here. I will try to describe them all and give you some details about everything, hopefully. But at any time, feel free to ask if you have questions. Especially, I'm not very good in writing, so if you don't understand anything, please ask me. So the talk will be mainly based on this recent work, but also towards the end I will mention some results that we obtained in this previous work in collaboration with Gleb, Giulio and Alessandro were here, and Alba that was here last week. So okay, first of all, let me start by saying that in general, it is since 2003 that Kodama and Ishibashi used gauge invariant formalism to describe gravitational perturbations around maximally symmetric spacetimes in generic dimensions. And in particular, the idea is that if one considers, let's say, a 2 plus n dimensional manifold, where these two essentially encodes time and radial direction, and n is the dimension of some internal manifold Kn, which is maximally symmetric in the sense that it has a constant sectional curvature. Capital K, then the gravitational perturbations around this spacetime can be classified in terms of harmonic tensor decompositions over this manifold Kn. And in particular, we encounter three different sectors of gravitational perturbations that I list here. So we have a scalar sector, vector sector, and the tensor sector. So tensors actually are there only for total dimension greater than 4. But if you want an easy example, if one just consider, let's say, the case n equal to 2 and lambda equal to 0 and k equals to 1, this is the case of 4-dimensional Schwarzschild black holes, and the gravitational perturbations are just encoded in two types of gravitational perturbations that are the Zerilli and Regge-Wheeler perturbations, as we well know. So in our description, so today I will focus, and it's written here in the title, on the case of planar black holes or black branes, which is the case where k is equal to 0, and also we'll be dealing with asymptotically AdS spacetime, so we will just take lambda to be some negative quantity. And first of all, I will start by talking about the bulk 5-dimensional problem. So instead of using this representation for the dimension, I will now turn to describing b plus 1 dimensions, where b, in the case of AdS, is the dimension of the CFT living on the AdS boundary. And we will start by considering the case t equal to 4. So we will consider planar Schwarzschild AdS black brane, which, as you well know, it's dual to n equal 4 super young means. And so let me start by writing the metric of this spacetime. Okay, so this is the metric that we will consider in particular here. So we define a radial variable z, which can be written in this way. So it's the square of this quantity where R0 basically encodes the position of the black hole horizon, and R is the standard radial Schwarzschild-like coordinate. Then this term over here stands for the three special directions, so can be expanded like this. And then R is the radius of AdS, which will be just set to be equal to 1 in all the computations I will show. And finally, T is the Hawking temperature, associated with the black hole horizon. Yeah, and finally I have this blackening factor f of z in this z variable. It's very simple, it's just 1 minus z squared. Okay, very good. And by looking at this variable in particular, we have that z equal 1 will be the location of the black brane horizon. And z equals 0 is the position of the AdS boundary. Okay. So I will talk about later also about scalar perturbations, but the main sector we will deal with is the case of vector sector of gravitational perturbations. And the vector sector can be described by off-diagonal perturbation to the matrix of h mu nu, such that these two components are non-vanishing. So ht x1 is non-zero, and the same thing for h x1 x3. And as I was mentioning, how to describe these perturbation in terms of only one master ordinary differential equation in the radial direction is basically based on the work of Kodama Shibashi. Moreover, we will not be interested in a generic class of vector perturbation, let's say, or the generic sector represented by vector perturbation, but we will be mainly interested in computing the dispersion relation of the so-called shear mode. In particular, there is a specific regime of this perturbation, which is the low frequency and long wavelength regime, in which these vector type gravitational perturbations can be described in terms of hydrodynamic processes that live on the boundary of the AdS space-time we are considering. And in particular, the vector sector in this regime reduces to, so one gets the shear mode, the shear mode dispersion relation. So in hydrodynamics, the shear mode, it describes fluctuation of the transverse velocity where with transverse I mean transverse to the wave vector. And in addition to the shear mode, there is another hydrodynamic mode living on the dual CFT, which is the sound mode. instead describes the fluctuations of the longitudinal velocity together with, let's say, fluctuations of the energy density and pressure. But the sound mode is obtained by taking the hydro regime of the scalar sector of gravitational perturbation. So we will come to this later because it's a bit more complicated, but this will be the main character of the story. And so in particular, we will restrict to study the shear mode for the main part of the talk. Okay, so now I described the gravitational setup we are interested in, but I have to give you the differential equation that is from which the dispersion relation for the shear mode can be obtained. So this is one of the two long equations that I have to write, but I think it's the explicit expression of these ODE is not super important, but I will discuss some important details about it. So bear with me for a while. So as I was saying before, the whole complexity of the problem can be encoded in a single ordinary differential equation, which essentially describes the radial part of the perturbation in this redefined variable z. And here I only introduce two additional variables. So omega is the frequency of the perturbation, and q is the norm of the wave vector. And both these quantities in these differential equations are defined in units of 2 pi temperature. And finally, the whole differential equation is written in terms of master variable psi, which is obtained by doing some redefinition of the original variables describing the gravitational fluctuations. And in particular, the only thing that will be important is that to get the quasi-normal modes of this problem, and in particular the shear mode expansion, I have to provide two boundary conditions to these second-order differential equations. And in terms of this master field psi, this will just be regularity conditions at the black brane horizon and the AdS boundary. So I will ask psi to be regular. Equals 0 and at z equal 1. So the regularity at z equals 0, which will encode the normalizable boundary condition in the AdS boundary, whereas the regularity at z equal 1 stands for the presence of only ingoing modes at the black brane horizon. Okay. Yeah, and the other important thing is that this is the main regime we're really interested in, and what I mean by this is that, in particular, Q is basically the inverse of the long wavelength. So these two parameters here, these two omega and Q variables, are assumed to be small. So in particular, we will consider the small Q regime and consider an expansion of omega made like this. Where, in particular, the series ansatz for omega in even powers of Q starts from k equal 1, meaning that omega goes to 0 as q goes to 0. And moreover, the idea is that we will solve the differential problem order by order even powers of q as well. Namely, we will also put the same ansatz on the wave function side, but this time starting from k equals 0. Okay, so this will be the setup of our problem, and the goal will be to find analytic expressions for these coefficients omega k, which we want are called transport coefficients. Okay, now let me take just a step back and focus for a moment on the differential equation itself, because there are some important things we can learn from this expression, and also some comments that will motivate the way we will proceed to solve this particular problem. So first of all, if we study the singularity structure of this differential equation, one can recognize that this is a Hoyne differential equation, namely it has 4 regular singularities, 2 of which are the ones where we impose the boundary conditions, so representing the AdS boundary and the black-body horizon. But then we have 2 other regular singular points, which are at z equals -1 and z equal infinity. So yeah, maybe. Yep. So there are 2 pictures that I want to draw just to represent this singularity structure. As my collaborators know very well, I like these kind of pictures because I think they tell you something about the problem you are considering. So first picture I will draw something like this. So this will represent the z-space of our differential problem, and in particular the z-space is a 4-punctured sphere where the punctures are located at the positions of the regular singularities. But here I'm representing the 4-punctured sphere as, let's say, it spans the composition, meaning I'm representing it as a union of 2 3-punctured spheres. And moreover, I'm putting 0 and 1, so the positions where I'm imposing the boundary conditions on the same patch of this decomposition. Namely, I'm selecting one possible decomposition of the singularity structure that is easier to impose both boundary conditions in once. And I will come back to this later. And also an alternative picture that will be used to later is just representing in the, let's say, the complexity plane the singularities as this, where I'm drawing the unit circle, and then of course we have the singularity at infinity. So why this is important? Forget for a moment about this specific regime, and one can ask for solving the quantization problem for the quasi-normal mode frequencies in general by considering this differential equation and imposing the 2 boundary conditions. And if you give me a specific overtone number for quasi-normal modes and a value of q, I can try to solve for the specific q and m located at those values of q and n. And in particular, there have been many recent developments about solving the Hoyne connection problem. So in particular, let me to cite the work by Cristoforo, Giulio Alessandro, and Daniel, 2022, and also for specific problem that I will talk about in a moment. There has been an equivalent method described by the work of Lisovi and Nephew. So in particular, the idea is that we have 2 boundary conditions to impose, and we can start by selecting the local solution around one singular point. For example, let's take the regular solution around z equals 0, and we can express it as we then analytically continue it towards the second point where the second boundary condition is imposed. And so we can write it as, say, so we can represent this solution as a linear combinations of the local solutions around the point z equal 1, and then just by imposing an additional regularity boundary condition there, we can solve for the quasi-normal mode frequencies by asking one of the two connection coefficients to be equal to 0. So these formulae rely on series expansion in the so-called instanton parameter, namely both techniques rely on connections with two-dimensional UV conformal field theory and n equal to 2 supersymmetric gauge theories, which are dual to each other thanks to the AdT correspondence. So I will not talk about this setup, but I just want to mention that in this case, the instanton parameter is essentially the position of the fourth singularity in the problem, which is -1. Up to some transformations, it can be put to be equal to 1/2 or 2. But the important point is that they are series in a finite parameter in the game. So it is not a small parameter that you can argue that adding more contributions to your series ansatz, you will correct in a good way your ansatz for the connection coefficient. At each time you will correct every order of your expansion. But still, if you provide enough instanton, the procedure converges. So you can show that you are inside the radius of convergence, and in particular, just by solving this problem, which locally is similar to a hypergeometric-like problem, and this is the procedure that also Rodolfo talked about last week, you can show that you can really find a good numerical agreement with, for the gap quasi-normal modes that you would find just by solving numerically this ordinary differential equation. So this is in general for solving the problem of Q and M, but in our case, we have a small parameter in game which is Q, which has nothing to do with the position of the fourth singularity, and so we have to abandon this method. So this method will not be effective for our specific problem. And we have to solve the problem in some different way. And the way that I propose is basically the following, namely, as I was saying over here, solving the differential equation order by order in Q. So the leading order is quite simple. Since both Q and omega are small in the regime we are considering, we can just impose them to be 0 in the differential equation and solve for the leading order expansion, and one finds the following basis of leading order solution. So this is basically solving the ODE at Q and omega equal to 0, gives the following basis of leading order solutions, where you can see immediately that this G0 is what I would call the discarded leading order solution, because it is not regular at z equals 0 and not regular at z equal 1. And so this will be the selected leading order solution. And this is the solution of the leading order problem, of course, telling you nothing about this series because we fix omega to be 0 at leading order. But then you can proceed inductively and solving order by order for these corrections psi k and the transport coefficients omega k. So the idea is that one just uses the method of variation of parameters, and namely we can write, and this will be the second long formula that I write today.
Sorry,
Yes,
does it
please.
says that Q equals 0, for Q equals 0, omega equals 0 is a Q and M?
So this is specific for this sector of perturbations, namely from the AdS CFT correspondence, you have that in this infrared regime, there is a hydrodynamic description to the problem. Namely, you can see that these sectors of perturbations admit a realization as hydrodynamic diffusive processes, which are the shear and the sound mode processes.
Also, like for Q equals 0, you have a properly real Q and M at omega equals 0.
What do you mean by real? Because they will be imaginary, so I don't know if...
But that means like if Q is equal to 0,
Yes.
then omega equals 0 is a solution of your Q and M condition.
Yes.
And so you have a real Q and M at omega equals 0.
Yes.
Ah, okay.
Yes.
Okay.
Just one brief comment. If you start from the tensor sector, for example, and you try to do the same, you will not find dispersion relation for hydrodynamic mode in this sector. These are the only two which admit this serialization. Okay, sorry, we'll go back to this. Okay, so with this method, essentially what we are saying is that each order k of the solution to the differential equation can be constructed from the previous order solutions. And in particular here we have the dependence on the basis of leading order solutions, so psi 0 and g0. Omega 0 is simply the Wronskian between these two solutions. And in this case it's just a rational function. Then, since this is a second order differential equation, in principle we would have two integration constants, but one of them would just be some overall normalization for the wave solution, so it would be some term of this form but with psi 0 instead of g0, so we can just fix these integration constants to 0 because they will just affect an overall normalization. And so we remain only with one integration constant in front of the discarded local solution. And these integrals indeed can just be taken to be the indefinite integrals because we already introduced here all the appropriate normalization. And finally, I have to tell you what eta k is. So essentially, eta k is the inhomogeneous part of the differential equation at order k. Namely, you imagine to have solved this problem up to order k minus 1. And you just take the inhomogeneous part of the differential equation at order k that remains. So I don't know, to me it was useful to write it down, this formula, some schematic formula in the Wolfram mathematical language. I don't know, it will be clear, but hopefully. So you just take your ODE by taking the series ansatz truncated at order k. You take the order 2k in the expansion of Q around 0, and you just set to 0 the dependence on the k solution, and you remain just with something which depends only on psi 0 up to psi k minus 1 of z, which defines your eta k. So this is everything you have to do, and finally you impose your boundary conditions, so z equals 0 and z equal 1 to these ansatz. The first boundary condition will fix the integration constant ck, and the second boundary condition will allow you to get the analytic expression for omega k. So the problem is solved. No, the problem in this is that, of course, this is the difficult part, taking the integrals of this formula. And the reason for this is that if you just start with this leading order solution and you ask Mathematica blindly to solve for this order by order thing, you can do it at first order and you get a very simple answer for omega 1, which is equal to minus I over 2. But then you have to basically stop. So Mathematica is not able to take the integrals of these functions at higher order. And so you have to come with an alternative method that is essentially the crucial step that we take. And the idea is that instead, so the basic idea is that taking derivatives is easier than taking integrals, of course. And so the idea is that we build some ansatz for the resulting integrals coming from here. And if we have some, let's say we order by order in K, we build up a basis of local solutions that can appear in the expression of psi k of z, so that once we take derivatives, we match these two integrands. And therefore, once we determined all the, let's say, undefined constants a priori in our ansatz for psi k, we can argue that this order for the solution has been solved. And how do we impose these generic ansatz? This is possible to do just by analyzing the singularity structure of the problem at leading order. Since we have to deal with a recursive problem, essentially all the seeds that allow you to solve order by order this problem are encoded in the leading order description. And in particular, what I will just give you the answer, and the answer is that in general, in the expression of psi k of z, we will encounter multiple polylogarithms in several variables. So we just denote multiple polylogarithms in this way. And these are functions that admit the following Taylor series expansion. So in particular, they are defined via a set of natural numbers S1 up to Sn, and they depend on n variables z1 to zn, and they admit these Taylor series expansions. And we will call the sum of these natural numbers the weight of the multiple polylogarithm, and n its level. And why these are the functions that solve our problem? Essentially, the idea is that you can define these functions in an alternative way, which relies on iterative integrals. But again, instead of giving you the expression in terms of iterated integrals, I find it more useful to give the recursive relation that they satisfy written down in terms of derivative relations, which reads as follows, and it's divided in two cases. So the first case is the one in which the first index S1 is equal to 1. The second case is instead for S1 greater than 1. So the idea is that we act on the multiple polylogarithm with this derivative operator. And in the case in which S1 is equal to 1, we get a multiple polylogarithm with lowered both weight and level. In particular, we will always decrease the weight by acting with this derivative operator. But in this case, we also remain just with n minus 1 integers and n minus 1 variable, the first one of which is the product of the first two variables that we had in the original multiple polylogarithm. In the second case, in which S1 is greater than 1, acting with the same derivative operator, we are just lowering the first index by 1, and all the rest remains the same. And the starting point of this recurrence relation is essentially just the fact that the first polylogarithm is essentially the standard logarithmic function in a trivial way, let's say. So just by recognizing the iterative structure that we are describing here, one can realize that these are all the functions that will appear in the expression of psi k of z. But we can say even more, in the sense that we can be more restrictive on describing the set of solutions, the set of functions that can appear. And in particular, at order k, we will include in our basis of functions for psi k of z only multiple polylogarithm with total weight less than k, or actually we can be even more restrictive, namely we will build here a linear combination of some monomials. For example, we can have also something of the form like a product of a multiple polylogarithm times an ordinary logarithm, and these will have weight equal to 4. No, weight equal to 2 plus S1 plus S2. So we define the total weight of a function that we include in psi k of z to be the sum over the weight of the multiple polylogarithm and the powers of logarithm that multiply them. And only functions of weight less or equal than k can appear in the expression of psi k. And also we can put some constraints on the possible variables that enter our multiple polylogarithm. And in particular, we have that the variable from z2 to zn can only have values in 1 and -1. And this has to do with the fact that this is the singularity structure of our problem. And the first variable has values in plus or minus z if S1 is greater than 1, but for convergence reason, for this Taylor series expansion, Z1 can just assume the value minus z if S1 is equal to 1. So with some other details that I will not talk about, the idea is that we have an answer for all the functions that can appear at each order. And also, the other important thing that one has to specify is that these functions satisfy some non-trivial identities between them. Some easy example of identities, for example, is already this first definition of the first polylogarithm, which actually is just an ordinary logarithm. Other kind of identities can be found just by looking at the iterative structure here and defining multiple polylogarithm as iterated integrals. And if you then integrate by parts and you shuffle, in some sense, the integrals that you are taking, you can write some linear identities between multiple polylogarithms of the same weight. And then there are more complicated identities involving also products of different multiple polylogarithms. I will not talk too much in detail about this, but this is an important aspect because at each order k, the difficulty of taking this integral will be replaced in our problem by specifying the basis of solutions and finding all the needed identities. So once you have this, you come back to the problem, and again, you just build your ansatz, you take derivatives and solve for a linear system for the coefficients in front of monomials of this form. And in the end, after you have reconstructed these two integrals, you just impose your boundary conditions and solve for the integration constants and for the transport coefficient. So in this work, we computed the first 5 orders of omega k. And just to give you a taste of the result. So I already wrote the first transport coefficient. Then, for example, I will not write down the whole expression, but for example, omega 4 contains in this expression the dependence on the value zeta 3. And omega 5, which is, as far as I know, a new result in the literature, has the following forms. So the expression is much longer, but I just want to underline the fact that here we have, for the first transport coefficient who has explicit dependence on some multiple polylogarithmic structure. This is not precisely of the form that I described here, but the point is that since there are non-trivial identities between multiple polylogarithms, this is the shortest version to which you can express your omega 5, and it is not possible to re-express this number in terms of simpler irrational numbers. And then you have these also complicated structure of products of zeta values times logarithm of 2. But there is a lesson that we can learn from here and a characterization structure for the transport coefficients. Indeed, the point is that at each order, we know precisely what are the functions that appear in the expression. And by imposing the boundary conditions, one can see that the transport coefficients can just be obtained in terms of these functions evaluated at z equal 1. So you can recognize that logarithm of 2 just come by setting here z equal to 1. And these zeta values, or more in general, multiple zeta values, arise just by setting z equal to 1 inside these multiple polylogarithms. And in particular, there is a characterization result for these transport coefficients that says that all their expression just depends on what are called colored multiple zeta values evaluated at second roots of unity. Which are just these 1 and minus 1.
Can I ask?
Yes, please.
The number of basis functions, I imagine, grows with
Thanks
the
a lot. That's very, yes, absolutely. So, yes, the difficult part in this process exactly is not only to determine this function and their identities, is the fact that these functions grow exponentially with the k. And this is, the idea is that essentially at each order, you can decompose your so how you guess for the resulting integrals from here is that you decompose in partial fraction decompositions your integrands, and you can see that the whole pole structure is essentially given by taking integrals over these three things, because all higher powers can be decomposed in some simpler way. And so at each time you are increasing let's say the level or the weight of your function by integrating against this pole structure. And so you expect the number of multiple polylogarithms in psi k of z to grow in this way. So some exponential with power 3, with basis 3, sorry. Okay, so.
And how long does it take to compute, to run the program and compute?
Okay, I'm not the good person in writing program, but this is almost immediate, because in the end it's just solving a linear system of equations for the constants that you put undetermined in front of your ansatz. The difficult part is
like
indeed. I mean, I did up to order 5. So if you want to go very high, of course, you will need more like large memories and time, of course. I would say, however, that the longest part is probably something that you have to do probably by hand, that is building up these functions, well, a basis ansatz for your function and compute the identities between these functions, which I think mathematically is also known probably because of Feynman diagram computations. But yeah, I basically had to do it by hand, so it was the longest.
Is it feasible, like, to compute a sufficient number, for example, to see the growth of the coefficient?
That would be the dream. I think you can go farther. I don't know how much farther you can go. I would expect maybe one can go up to omega 10 with enough time and memory. My hope was more that having a complete characterization of the transport coefficients in this way, maybe there is some kind of, I don't know, bootstrap way or some generative function that can be found, and so that you can generate all of them and then study, for example, the radius of convergence just by having, if you have the closed form expression, of course, but I mean also to generate many of them. Yes, please.
Yeah, speaking of this program to generate these series, I mean, like in the WKB literature, you often do like these differential operators at each order that you construct to avoid actually doing the integral. Could something be done here in this way to speed up, particularly since you also know more or less the basis of functions you're working with, so that maybe the differential operators could be just written as in like fairly straightforward matrix?
Okay, yeah, to be honest, I'm not sure. Of course, here, let's say that at this level, there's nothing new in the sense that this is just a standard way of solving the differential equation. And of course, I'm not the one that built this machinery. How to make contact with that, to be honest, it's not clear to me.
Because, I mean, yeah, with the differential operator method, I think people can usually go to fairly high orders. I mean, it does rely on some specific structure of the problem, but with this, it'll, yeah, it seems similar. I don't know if you had considered it.
Yeah, I'm not too familiar with it, but yeah, it would be nice to discuss. Yes, please.
Yeah, I just have a couple of comments. I think this series that you are showing is very similar to the one series in quantum mechanics, right?
Okay.
Starts solving your
Yes.
directly evaluating some expansion parameter, and actually this kind of approach was used to compute love numbers for scalar perturbations of quantum numbers by Simon or collaborators, right? Like then we see explicitly how these multiple polylogarithms appear from this kind of iterative way of constructing these integrals.
Yeah, I think the idea, essentially the underlying mechanism is precisely the fact that you have a Fuchsian differential problem with only regular singularities, and so around each regular singularities, if you expand in series in a small parameter your problem, you just encounter multiple polylogarithms. If you had some irregular structure, you would have to generalize those functions to include also exponentials and iterative integrals of exponentials.
Yeah, in that case we have this exponential.
Yeah.
Like the homogeneous problem you have is Bessel functions that you do this
Yeah,
integral Bessel
exactly.
function. But now speaking of this W function, W transport coefficients, now the problem looks very similar to what Dimitrius, Cosmopoulos, and Picasso did, which was like extracting love numbers from solutions directly from the solutions of the wave equation, like MST, and then like basically the love number, which is kind of the analog of the reductive. So here they were like there was a explicit formula that was basically like very similar to evaluating the MST solution provided by some Ruskin. The nice thing about that work was that they recognized like a universal part of these love numbers, and then they always come with these zeta numbers, and they kind of pre-sum, they predict what this universal contribution of this number would look like. Maybe something similar you can do with your transport coefficient. Maybe not recognize the whole series for the numbers, but maybe there is kind of universal contribution that you can resolve.
Thanks.
It's
Yeah.
very similar to
Yeah. Would be nice. For example, I know that these functions were already expected to appear, so there are some vague results on saying, okay, this kind of function like lead 2k of 1 alpha to appear at, I don't know, order like k plus 1 or something. So yeah, there is some structure behind that. It's probably expected. But yeah. Thank you. Yeah, other questions or? Okay, so everything I said up to now was restricted to taking the 5 dimensional case, but everything that I said can be generalized to generic D-dimension, because it essentially I started from the Kodama-Ishibashi formalism, which allows you to go to generic D-dimension. And what changes in this case? So, of course, the first thing that changes is the differential equation, and in particular the singularity structure that will be more involved. And in particular, there is a distinction between cases in which lowercase d is odd or even. So we have d plus 2 or d over 2 plus 2 regular singularities. This is for odd values of d, and this is for even values of d, where d over 2 or d come from the zeros of the Blackening factors, so f of z equal to 0, where also the variable z is different in the two cases. Namely, you can define something like this if d is even, or you can just remain with 1 over r in the odd case. So this was the case we were before with d equals to 4. In the odd cases, you cannot define the quadratic transformation for your differential equation, and you have to stick with d plus 2 regular singularities. The 2 instead comes from z equals 0 and z equal infinity regular singularities. So in terms of this picture over here, this was the picture for, let's say, the Hoying connection problem or NF equal 4 supersymmetric H theory. And the problem from that point of view will generalize to an n equal to quiver gauge theory, with the length of the quiver that increases if you increase the number of dimensions. However, it is still possible that, to arrange the singularity structure in such a way that the two singular points z equals 0 and z equal 1 remain on the same patch, and then you just take the quiver to be longer on the other side and maybe more complicated, but you can still solve the differential problem on the same patch. With this I mean that the whole procedure now works the same way, and you can still impose both boundary conditions to the same psi k of z. And the functions that you will encounter will be, again, multiple polylogarithm. What will change is this characterization over here. So instead of having z2 and zn to have values in -1 and 1, this will have values in, I denote the set ui, where ui is the set of either d over 2 or d roots of unity. And z1 will have value in, say, ui times z, where ui again are all the roots of unity. In the case of S1 equal to 1, you can take all of them, if you want, apart from the last one, which represents just the variable z. And in terms of the number of functions that you have to include in your basis, as you were pointing out, instead of having the growth like 3 to the k, we still have an exponential growth, but of course this will depend on the number of singularities. So you will have 1 over z, and then here instead of 2, you will have d over 2 or d. So let's say that this will be something like 1 plus d over 2 to the k, or 1 plus d to the k, for the number of functions that you have to include in your basis. Here the singularity structure will look, let's say, you will have more singularities arranged to be a regular polygon like this. But the same conclusion also holds true for the transport coefficients, that will be still colored multiple zeta values evaluated at roots of unity, where here this will just be d over 2 or d roots of unity. And so you have a whole characterization for the transport coefficients in the shear sector for any generic dimension d. And of course, with more solutions to add to your basis and more identities to be computed. And yeah, in the paper we show the example of lowercase d equal to 3, so the bulk 4-dimensional case where you have third roots of unity. Okay, yeah, there are other questions to this point. So I will just take one additional step, the last one. So everything I said up to now was for the shear mode. What happens for the sound mode? So the sound, the expansion of the sound mode is more complicated, and in particular where this reasoning fails is that if you start from the Kodama-Ishibashi formalism, you will have additional singularities in your radial differential problem. And the idea is that now you can no longer, you can again put some ansatz of this form, but if you try to impose both boundary conditions at once, you will fail. So you can impose one of the boundary conditions, but as soon as you try to impose the other one to get the result for omega k, you will find some divergences or some inconsistencies in the process. And the idea for this is that, for example, here you will have some other singularities lying over here, and if you try to continue from here, from z equals 0 to z equals 1, you will be stuck by the fact that you encounter other singularities in your problem. However, it is still possible to solve the problem in a similar way, and this is the point where I want to talk about the previous work with Giulio, Alessandro, Gleb, and Alba, in which we solved which we obtained the sound mode expansion for the bulk 4-dimensional case. So we started with the spherical Schwarzschild AdS for black hole. And we started by computing the expansion of omega in inverse powers of the radius of the black hole horizon. So this is the regime, because in the end we want to connect to the planar case, but we started with the spherical problem, and then we took a large black hole horizon regime. And in order to solve the problem, we had to introduce different local regions. So we took one region that is essentially represented by this picture, but with the third roots of unity. So let's say just this kind of polygon, if you want. And this is for the region close to the black hole horizon, where all this machinery works. So you construct multiple polylogarithms in terms of third roots of unity. And then you solve in an analogous way the local problem in the near AdS region and in an intermediate region, where both the expansions coming from the AdS boundary and the black hole are convergent. And there you just impose the Wronskian to be equal to 0 to glue the two solutions. The nice thing about this approach is that this problem is as much complicated as it was before, but the other two problems, the local AdS boundary expansion and the expansion in the intermediate region, are very, very simple in the sense that they can just be solved in terms of rational functions. That's all that appears in the expansion of psi k of z. So the whole complication comes from this region close to the black hole horizon. And then what we find once we have this expansion over here is that we take the double scaling limit in which we send to infinity both the angular quantum number and the black hole horizon in such a way that we define this. So we take to be fixed these ratios representing the norm of the wave vector q and the new, let's say, frequency that we call w. And we put again the same ansatz as before of omega in powers of q. This time, since it is for the sound mode, we don't have only even powers, but we have all the integer powers of q, starting again from 1. And we could solve for W1 up to W7, so the first 7 transport coefficients. And so in the shear mode, all these transport coefficients are purely imaginary and negative for stability reasons. These ones alternate between purely negative imaginary numbers and purely real numbers. But they have the same structure that I described here. So they can be completely described in terms of colored multiple zeta values at third roots of unity. And the idea, I think, is simply because essentially this is the only difficult expansion and the other rational expansions do not bring more complicated irrational numbers in the game. However, this is not really a proof for the sound sector, so maybe there is some more rigorous proof to be done there. This is very apparent since we can impose the conditions on the same function expansion. So this is more or less everything. Let me just conclude by giving one additional outlook maybe. So I already discussed more or less the importance of having the complete characterization of these irrational numbers and the hope that maybe some generating function can be found to completely not only characterize, but also to have maybe some good estimates, for example, on the radius of convergence of these dispersion relation. And also I think there is an interesting limit would be the d to infinity limit, because there have been many results for the large D expansion, like Ben, Emparan, or Sasho. And in particular, in these problems, you have an additional scale in your problem, which is, let's say, an expansion in 1 over D, where things simplify dramatically. But from this point of view, or also from the supersymmetric gauge theory point of view, this would be the limit of an infinite quiver gauge theory, but with the quantization condition that it's still given, if you want, by the quantization of the composite monodromy around these two singular points. So I think it would be interesting also to understand how the d-infinity limit affects the expansions that we know in the gauge theory language. Namely, this composite monodromy in the Hoyne case is just an expansion in one instanton parameter. If you take a longer quiver, it will be a series expansion in all the instanton parameters in the theory. In the d-infinity limit, it will be something quite difficult to characterize, but in principle, it must be something simple from the results that we know from this regime here. So I think there's some interesting story happening there as well. And with this, I think I can stop. Thank you very much.
Thank you, Paolo. Maybe I really have a question. I'm also connected to the paper possibly that you and Ben posted today. Is there any chance to recover these numbers from the CFT, and would you expect that they are connected to the double trace OP coefficients?
So, kind of a short answer is, I'm sure the things are connected. In what precise way, I have no idea.
Okay.
In the sense that, yeah, I think something can be said. So in this program, we work in the Euclidean version. So this is, everything is Lorentzian here, but I think the formulation of the problem can be understood more or less in the same way. If there is some alternative method that analytically allows you to get this kind of expression, may be possible, but yeah, I'm not fully sure. But maybe there is something that, like using this expression, maybe tells you something about expressions of the double traces. This would be interesting, of
Just
course.
because I think that the consensus is that these double trace coefficients, OP coefficients, kind of govern the daytime dynamics. So also, since you're computing transport coefficients, but I'm also not expecting the connection to be super.
Yeah, I think it's not immediate, but I think it's something to think about definitely. Like I think, I'm sure that some, let's say, analytic structure in common is there. Like just for, you can see also from your work, you know that these zeta values or polylogarithm appear in these kind of expansions, and this is not, let's say, random. It's there because of the singularity structure of the problem, which is the same for both problems. So I think that the two analytics, the same underlying analytic structure can put the two things in comparison. Now, yeah, unfortunately, I don't have anything more sharp or clever to say at the moment.
Okay. Thank you. More questions?
You comment slightly bit on something tangential to this, but sorry, this might be too speculative. But I mean, this polylogs of 1/2 and 0.3. I mean, there's also, I mean, there's a very similar story in like string theory by I think by Aldai and company.
Yeah,
and also in like classifications of Feynman integrals is also a very common structure. Do you have like a broader picture why this problem fits into the same class?
Okay, to be honest, not. I think, okay, as you mentioned, yes, I would say that from the physics point of view, this mathematical structure was studied precisely for Feynman diagrams computations. And I guess the main reason is that you are studying some spectral problem which has the form of some, I would say, differential equation with only regular singularities or something like this. This is essentially some kind of, if you want, even just hypergeometric problem without talking about Hoyne, because you're basically just restricting here, then you have some other more complicated stuff in the story, but that's not the main important thing. About this polylogarithm, one thing that I could say is that you can, I think the result is that you can express all the multiple polylogarithm up to weight, I think 5, only in terms of classical polylogarithm, without having level higher than 1, in the terminology I described. So, but yeah, of course, the variables that you will end up with will be more complicated. These are called the Stafford relations between these functions. So yeah, I would say that also from the computational viewpoint, there are many programs that are more, that are written down with the idea of computing Feynman diagrams more than solving differential equations. But
because, for example, I think it was all but that at least in the story, in the string theory, you can also, I mean, the combinations that you get between zeta functions and polylogs are very specific ones. The notion of extended zeta function. I mean, I'm slightly mumbling this from thought.
Yeah.
So I wonder if you try to check if you're getting the same basis, or like the same basis of extended zeta functions that they get in this.
I would say yes. Like it's not something different. Then the point, I think, the only difference maybe is that in this case you have only one set of colors, let's say, that you add to your multiple zeta values. That depends on D. In that case, I think you can have multiple of them at the same time. But essentially, yeah. They rely both on the same class of irrational numbers, yes.
I had a similar question, but so in string theory you see these appearing amplitudes for any number of points, right?
Yeah.
And what you write there, your picture looks like a 4-point amplitude.
Yes.
But you could add more points. What would that mean for you?
Yeah, this is yeah, I think you're right, and this probably also partially answers Tomas' question in the sense that, yeah, as I was saying, if you increase D, you change this picture by including more punctures to your sphere, and so it seems like you're having an amplitude with more points or more punctures in the game. So yeah, that may be related. I agree. Yes. But then maybe in the Feynman diagram computation, you can also consider just one subset of the punctures and having at the same time different colors for your multiple zeta values. I'm not sure, but yeah, I agree with the comment. Yes.
Well, I think you're comparing a two-point function, right? I mean, the question of was about maybe you have a three-point function in the background that's going to be higher point.
Ah, I see.
Yeah.
That should be like non-linear perturbation theory. Totally linear.
Yeah, let's say that essentially this is, so here we are solving some inhomogeneous differential equation because of you can think of this eta as the source to your differential equation. So
The differential equation that you get by doing linear method.
yes. But
If you do second order perturbation, you will get things like
yeah, you will have in the source on top of this, you will have products of two linear order solutions times the source. So you will have three things appearing inside the integrals instead of two. Yes, in the quadratic level, for example. Yeah.
those are the
But I would say that also in that case, like if you stick with the same dimension, let's say we work in the bulk 5-dimensional case, even if you add other things inside here, you end up within the same realm of irrational numbers and multiple polylogarithms. It's only that the structure will be more complicated and you have products of multiple polylogarithms. Then you can use what are called Schaffner relations, just to write them in terms of linear combinations of multiple polylogarithms of the weight equal to the sum of the two weights of the product that you're taking. But you still end up with the same colors here. So I think that it's changing D that allows you to pass to different families.
Really, a more formal question. That is it clear? So your expanding is more Q.
Yeah.
You don't really have a pair of pent decomposition here, right? Because
Exactly.
like,
Yes.
doesn't really. What are you expanding around? From like a singularity structure.
I think you are essentially just seeing the problem in this patch here, but you are not, let's say, close to 1 or close to 0. You are just inside this patch, basically. Or if you want,
For
you
example, when Q is equal to 0, how
Yes.
does the singularity structure apply?
no, it's always the same. Like
You
this
don't get
is.
some trivial monodromy, some integer monodromy or something like that.
That's a good point. That's possible. Yeah,
The solution is
yeah,
very
maybe.
easy, so maybe you're at a polynomial point or something
Yeah,
like that.
yes, I agree that probably the leading order is very simple. You're right. I think you're quantizing in some trivial way the composite monodromy. Yes, I agree.
Maybe like
Yeah,
one of
also
the-
because I think I'm not fully sure, but the U parameter of the Hoyne equation, if you want, is something like this, if I remember correctly. So it's just set to 0 in the omega and Q 0 case, and the masses or the initial parameters of these singularities also just depend on. They are either integer or they depend on omega. That is, if it is 0, it's 0. So yeah, everything is trivial at leading order. But once you go to next to leading order, I think you are not doing anything
So could it
special.
be that you're expanding around one of the, since you mentioned, like, could it be that you're expanding around one of the Lewis fields to being degenerate or something like this?
For sure.
Yeah.
Something like that.
Yes. I think that's right.
So if I understood correctly at the beginning, you said that the Yoon equation with the instanton expansion doesn't give you the result on the nose.
Yeah.
Because I did show the integral. But for example, can you check omega 4, that is zeta 3 from the summing over instantons?
Yeah, okay, I didn't do the exercise. The exercise I did was for the gap mode instead. So that are not the low-lying modes in this sense, so they do not go to 0, but you have your mode omega n, which has some finite value at q equals 0, and then if you increase n, they just move away from the real axis. And what you can do is that, okay, you can add many instantons. I think the paper that I cited before by Lisovi and Nadjuk has a very concrete continued fraction expansion that is equivalent to the instanton expansion that is very convenient to do that computation. And first of all, it allows you to see that you are in the correct convergence region to the problem, which is something that I think was not fully appreciated before. And you can include many, many instantons. With many, I mean by the order of, I don't know, 10,000s or 100,000s in the recurrence relation. So very large number of instantons. And if you just compare with the numerics that you get from the differential equation, you agree to as many digits as you want.
That looks like to me the generating function you're looking for, because you just want to fit a number, you know what's the multiple of
yeah, I agree.
And that's,
the only problem is that in the end the procedure relies on truncating this recurrence relation at some order, and it's not that you're neglecting subleading contributions, you're still neglecting some finite contributions, so it's not a closed recurrence relation if you want, or a closed in the sense that you can say, okay, I truncate at order 100 and I can get omega up to omega 100. They are all encoded in the infinite recurrence relation.
but the series is convergent.
The series is convergent. There is no rigorous proof of that because we are working in the Nekrasov-Shaterashvili regime and it's the most difficult to access mathematically. But what you can try to do is you can take your continued fraction expansion, which is an expansion in, let's say from here it would be -1. You can do some change of variable and put 1/2 instead of -1. And you can then take many orders and do a Padet approximants of that. And you can see that this series precisely converges with like up to here, like you are really at the boundary of the convergence of your series. And the nice thing is that if you increase the value of q and of n, you are shrinking the radius of convergence of the series, but the limiting case is precisely this, so you are always allowed to do that expansion. But this is just, let's say, speculative, relying on Padet approximants and no mathematical rigorous proof for the limit.
Questions? If there are no more questions, we can thank Paolo for the very nice talk.